Hello everyone and welcome back. Now, in the previous lecture, we were introduced to our first topic that we'll go through in this math modeling lecture series, and that is optimization. Now, what we were introduced to in particular was single variable optimization. This probably feels familiar to you because it's really just a lot of the stuff that you did in an introductory calculus class. Now, maybe it came with a word problem where you had to actually sort of formulate the equation, but nonetheless, the process was mostly the same. You need to find the derivative and set it equal to 0, and you can even check if it's a maximum or a minimum. Now, in practice, when you are formulating mathematical models, usually they're not that pretty to look at, and unfortunately, they're not that easy to find the critical points of. Now, the topic of this lecture today is going to be on how we can numerically, or at least algorithmically, determine these critical points. And the way that we're going to do this is through Newton's method, right? So yes, that Newton, Isaac Newton, right? So this is a root finding method that is used throughout computational mathematics for a variety of problems. Now, I have already given a lecture on the analysis side of Newton's method, so proving that it converges and really deriving a lot of the properties. So in this lecture, what I'd like to do is do a high-level overview of the method and then apply it to an optimization problem. Okay, so the basic idea here is we would like to solve f of x equal to 0. Okay, so we have a single variable scalar function in this case. And on top of that, we might have a guess at the root. So let's say guess at root. Now, this is really an art in order to formulate the guess. Now, in some cases, you can just plot the function, maybe using Desmos or Mathematica or Maple or a variety of other programs, and sort of eyeball out where approximately the critical point that you're interested is. But nonetheless, let's imagine that we've got a guess at the root. Okay, well, let's suppose we have something along these lines, and let's say this is my x-axis right here. This is my function f of x. And imagine this is really, really, really zoomed in, okay? So that I'm actually not that far away if I say that my guess is maybe right here. Okay, so this is my guess, and this is my point f of x, 0. So again, I've really sort of blown up the picture here, but in reality, you'd be very, very close. It would look like this is actually the root. Well, with the notion of closeness, we can apply Taylor's theorem. In particular, we can approximate the function f of x near f of x, 0 using a Taylor expansion. And in this case, we only need to go up to the linear order. Okay, so I'm using the approximately equal here because I truncated my Taylor expansion. But remember, the whole goal of this thing is to solve f of x equal to 0. So if I set this equal to 0, this gives me, so if I make this an equality, I get 0 is equal to f of x naught plus f prime of x naught, x minus x naught. And I can rearrange that thing to solve for where my x should be. So this will give me x naught minus f of x naught over f prime of x naught. And what this does is it gives me a way of updating my information. So I said, I think that my root should be at x naught. And then I use Taylor's theorem in order to update this guess. I say, actually, I can refine that guess. And if I plug x naught into this equation right here, I will get a better approximation of that root. Now, how does this work graphically? Well, this is the equation of the tangent line at f of x naught. And so what this actually does is it draws the tangent line, as I have right here. So tangent line. And it starts here, and it traces us down to the intersection of the tangent line with the x-axis. So this, if we call this, say, x1, this would be my x1 value. Now, what you can see, just looking at my picture as a proof here, I've gotten much closer to what the root should be, right? I've moved in just by following along this tangent line. But now you can think about this, and you can bootstrap this idea, because I've updated my guess. My original guess was x naught, and I updated it to get a better guess, right? It's probably still not going to be exact, but it's a lot better than I had before. But that means that you can do this again. So I'm already too zoomed in. I won't be able to draw it again. But if I take the tangent line there, and I follow that tangent line all the way down to the x-axis, I can get another point that's even closer to the root. So I could get, say, x2, which is given by x1 minus f of x1 over f prime of x1. But then I've got another guess that's even closer. I've got x2. So I can bootstrap this. I can get x3 that's even closer. And in general, I can get myself an iterative process that hopefully keeps getting me closer and closer to the root of this equation. So what I can do is, if I know my guess now, that's my xn, I can get a better guess just by following this same formulation that I've laid out right here. And what this does is it generates a sequence of guesses that hopefully are going to converge to your root. Now, as I mentioned, I've done another video on this about the intricacies related to applying this method. It all really relies on your first guess being close enough, right? So if I started way far away on this curve, there is nothing that will guarantee me that I'm going to collapse into that root that I am interested in. So a lot of the game here is coming up with a good initial guess. And unfortunately, that's the hard part, right? This is the entire difficulty of using Newton's method. Now, as I mentioned, you can get around it with these single variable problems, where you could maybe use a plotting program in order to at least get a nice guess at what your solution. Okay, so to see how Newton's method can help us when it comes to optimization problems, let's go back to the pig problem from the previous video. Now remember, we were trying to determine what the optimal time to sell that pig is, given a bunch of variables, right? We lose money keeping the pig, but the larger the pig is, it will produce more value. Now here's how I want to augment this equation, okay? So let's work this out as an example. I would like to augment the equation by supposing that the growth rate of the pig is proportional to its own weight. Okay, so this is something that I can give you in words. And you can think about this and you can figure out that if W of t is the weight of the pig at time t, remember t was measured in days, well then the growth rate, now we hear the word rate, we think derivatives. So this tells us that the growth rate, the derivative of this thing, is proportional to the weight of the pig. Now, is proportional means equals to a constant multiple of the weight of the pig. In this case, C is a positive constant, so is a constant. And what we also knew from that problem is the initial weight of the pig. We knew that it started at 200 pounds. Okay, the question is, what should C be in this case? Well, okay, what we'll do is we'll draw on a little bit of information that we had from the previous example or from the example in the previous video. So we had that the growth rate was constant and it was equal to 5 pounds per day when we were 200 pounds. Okay, so that's how we started that problem. So what we can do is we can use that to estimate that C should be 0.0025. Pardon me, I put too many zeros in there. 0.0025. And where this is coming from is just solving this equation. I know that when W is equal to 200, so C times 200, this is equal to 5. So that gives me C is equal to 5 over 200, which is 0.025. So that gives me a nice differential equation, which is 0.025 W. Now, just like the differential equation that I gave you in the first lecture for the ski goggles, this is a separable differential equation. So you can actually separate out the W and the T components here. Right? So if I treat that dW dt as a fraction, then I can multiply up the dt. I can pull the W over to the left-hand side. And now I get myself into a position where I can do some integration. So this is going to give me the logarithm of W is equal to 0.025 T plus C. And I'm going to leave it to you to sort of rearrange this a little bit and figure out what the constant is coming from this W. But I'll go ahead and just tell you that W of T is equal to 200 e to the 0.025 t. Okay, so that is the solution to this weight growth problem, right? So the way that I augmented the problem, if you sort of step back for a moment, is I said that instead of assuming constant weight gain, I'm going to assume that the amount of weight that's gained by the pig is proportional to the weight of the pig, right? So it's a sort of percentage of the weight that's being gained each day. Well, now I have a new W, right? Remember last time it was a linear function. It was 200 plus 5t. Now it is 200 e to the 0.025t. And so this means that I've got a profit function now. So if I go all the way back and use the rest of the information that I had from that previous example, I get 0.65. So 0.65. I keep putting an extra 0 in here today, 0.01t. And then 200 e to the 0.025t. And then minus the cost is 45 cents per day. Okay. And we also have to remind ourselves that we are, of course, doing this over a positive time scale. Okay, so the goal here, again, remember, is to maximize the profit. Now, that means that we would like to set p prime of t equal to 0. So the first thing that we can do is we can first figure out what p prime of t is. So I get negative 0.01 times 200 e to the 0.025t, and then plus 0.65 minus 0.01t, and then in this case, I'm going to get 5 e to the 0.025t. The 5 comes from multiplying 200 by 0.025 from the derivative here, and then minus 0.45. Okay, so the first thing you should notice about this is that that is a pretty ugly equation. And in particular, this is a very, very complicated equation that you're going to that you're going to need to solve, right? It involves exponentials. It also involves polynomials. And so that means that this is a transcendental equation, right? There is no way of finding a closed form solution to this thing. It's not just going to be like the log of 23 or something like that. So the question is, how can we find out what the maximum profit is? Because we still have a problem that we want to solve. Well, so we want to solve P prime of t equal to 0. This is exactly the setting that Newton's method gives us to work in, right? We want to set a solution equal to 0. So here's what I did. I took that equation right here, right? My derivative equation, and I threw it into Desmos. Okay, so then when I plotted this thing, I get a nice little quadratic looking curve almost. I mean, it's not exactly a quadratic curve, but it certainly looks that way. And in particular, what I did, and what I urge you to do, is pause the video, go plot it, and figure out where you think the maximum of this is. What I thought is right around day 20 is where the maximum is. Okay, so that means that I've got an initial guess. I call that T naught. And that's around day 20. Okay, so that's what I said. I said, just by looking at the picture, I'm pretty sure that the maximum of this, the 0 of this function is around 20. Well, then what I can do is I can do the Newton update. And the Newton update here is given by the update for the amount of time it takes to get to the critical point is equal to the current guess and then minus p prime of tn divided by p double prime of tn. Now, if you're going to compare this with the formula that I just gave you for Newton's method, notice that we are setting a derivative equal to 0, right? That's why there's a second derivative down here. This is your original sort of capital F function. So be very careful about just the subtleties in here, right? I'm not interested in finding when the profit's equal to 0. I'm interested in finding the derivative of the profit is equal to 0. Okay, so here's what I did. I started with T naught equal to 20. And I'm going to write out some numbers for us, okay? So once I did this, I put n equal to 0 into this thing. I got out my calculator. I figured out what p prime of 20 is. I divided it by p double prime of 20. And then I subtracted that from 20. That will give me 19.475. Okay, now I've got a better guess at where my root is, right? It moved me a little bit to the left. It said it's not quite 20 days, it's somewhere around 19 and a half. So then I put T1 into the right side of this equation. So I said P prime of 19.475 divided by P double prime of 19.475, and I subtracted that from T1 here. That gave me a better guess at the root. 19.4 and then 68. Now what I want you to notice is the first 3 digits didn't change. Okay, let's do one more step. If I take T2 and I put it into this right-hand side, I take P prime 19.468 divided by P double prime of 19.468, subtract that off of this T2 value, and now I get T3, and this is equal to 19.468. I got all 5 of the digits that I reported didn't change on iteration, right? So maybe some of the ones on the end did. But what you can see is that if you did this again, you get 19.468. Again, maybe some of the other digits will correct, but look at that, right? I could actually just do this on a computer, on a calculator. I didn't even need to do any programming. There's no for loops involved. That was rapid convergence. And this is something that we see with Newton's method. This is something that I proved for you in the other video that I've done on Newton's method. You have what's called quadratic convergence. So you have this exponential convergence. You have a doubling of a number of digits that will become correct. And in this case, now we can see that we should sell the pig after about 19.5 days. Okay, so assuming time is continuous, you can sell the pig at any time. Well, at about 19.468 days, that is the optimal time to sell the pig, depending on or assuming this proportional growth. Now, there's one other aspect of this that Newton's method can help us with. Another piece of this is sensitivity. So maybe we'll tuck that right here. Now, remember, sensitivity is a relative growth rate, right? So in our case, we would like to know the sensitivity, maybe of the time to sell, so that's t, given this growth rate c. So maybe we have a little bit of uncertainty in our model. Maybe we don't know exactly what the growth rate here should actually be, this c value. So imagine the following, okay? So if c is equal to 0.02525, that is a 1% change from the value that we used previously. Now, what that means is I could go back through all of these and just repeat everything. The only thing that would change would be this 0.02525t up here. I could find the derivative, and I could use Newton's method to solve again. And in this case, this would give me that the time to sell would be about 20.021 days. Okay, so if this c value is a little bigger, that means it grows faster. And that means that you should keep the pig for a little bit longer because it's growing so fast that it's sort of beating the negative points of hanging on to the pig for so long. But that means that you can put this all together, this sensitivity, and this tells you, remember this was dt dc times c over t. You can estimate this dt dc by giving you just this 20 minus 21 minus 19.468 divided by c is equal to 0.02525 minus 0.025. Right? So that's just a finite difference, a secant approximation of this derivative. You know what c and t are, right? So c is equal to 0.025 and t is equal to 19.468. And that's going to give you, in this case, 2.84. So what that really tells us is that if there is a 1% change in this growth rate c, there is a 2.84% change in the time to sell this thing. So it's not a huge amount of change, right? It's only a 2% change. And you can see that at play right here, right? It's only going from 19.468 to 20.021. So it's not a whole lot of time. It's only a 2% change. And again, the way that we got that is we didn't actually compute any derivatives, right? We didn't have to worry about computing derivatives because Newton's method is really just giving us single values of these functions. But the way that we did it is we did it sort of the old school way, right? So this tells us that this is t of 0.02525 minus t of 0.025 divided by 0.02525 minus 0.025. Right? This is literally rise over run, nothing fancy. Right? It's just a secant approximation of the derivative. So as you can see here, of course, Newton's method is going to help you. Right? It can help you, and it can help you by giving you this optimal value of your profit function. Now again, everything comes down to that initial guess, right? If you wanted to try this again with, say, an initial guess of 2 days instead of 20 days, you'll see that things might not work as planned, right? It might be slightly more complex. So, of course, we have this sort of computational aid coming through from the graphing that needs to be included if you're going to apply this Newton's method. Okay, so when we come back in the next video, we'll start talking about multivariable optimization. So that's when you have more than one independent variable. So I'll see you in the next lecture.